for a nice workshop and giving me an opportunity not only to talk to you, but meet so many of my Indian colleagues. So what I'm going to talk about is indeed quantum dynamics, and I will be talking about a work which was done with my colleagues in Toulouse. Jeanne Colbois did most of the work. I know she's moving to Grenoble. Nicolas Laflorencie, who is in the audience, and I hope I will have time at the end of the talk to talk about more recent results with Oshmi Alda. So if you want to sleep for half an hour, you can just scan that, and then you will have all the slides. All right. So since the audience is quite broad, I will take a little bit of time to tell you about this phenomenon of MBL, as we call it, many body localization. I'm sorry for the experts in the audience. I will give you the motivation and the standard hallmarks, and I will also try to make a point about the recent controversies and current views on the field. That will take like half of my talk. The second half will be about the new results that we have in some very simple yet unexplored limit, which is the weak interaction regime. And also, I would like to say that Nicolas' talk on Friday will examine another part of the phase diagram, which are also very interesting results that we obtain. All right, so let's start with the beginning. Something you probably have all heard of, which is Anderson localization. If you throw one single particle in a random potential, like this Hoping term and this chemical potential term, and you take this epsilon I to be random, in one dimension, you will find that all the eigenstates of this problem are localized with some given extent of the eigenstate given by some localization length here, xi. This is well understood. This is called Anderson localization, and actually a very simple question that was actually on Anderson's mind a long time ago when he introduced them all was the effect of interaction. So in interaction, you can write that in the single particle language, in the Anderson localized of the language, as would be that term, but the idea is very simple. You know, if particles start, for instance, to repel each other in a many-body state, what will happen? So very naively, you think that if particles interact, they will somehow exchange information and so on, and that will favor delocalization and simulation. But as a matter of fact, this is true, but as a matter of fact, it was shown first perturbatively with some approximation, with some numerics, and there are more recent results on the exact point of view, that in fact, interactions are not enough to destabilize the Anderson localization insulator. It gives rise rather to a new form of localization, which is called many-body localization. So to summarize, if you have interaction here and disorder here, if you have no interaction, you will always get Anderson localization. And if you have interaction, you can either move to a thermal phase, as naive expectation would tell you, or to some new state of matter, which is called this many-body insulator. And here I'm putting a question mark because that's actually where we're gonna have new results. All right, so please don't hesitate to interrupt me, but I want first to give you some just the language and the main ideas of summalization. So first, mostly for practical purposes, we'll change from fermions to a spin chain. In 1D, this is exactly the same thing. So we will have just a spin flip term, an Ising interaction, which can be this delta scale, which is going to be the interaction, and then some random field, which corresponds to random potential. This is the same idea. So the two key players are the interaction term and the disorder, which, for instance, we take in a box distribution. And there is one special point, well, not so special as a matter of fact, but it has been historically special. So most of the studies started actually at fairly strong interaction of the size of the opening thread. And we will depart from this limit at some point. But let me tell you the main idea of what is a many-body localization. So you can have that picture in mind. So if you have a weak disorder, you expect, in fact, two families of eigenstate of this many-body problem. You expect a family at weak disorder, which are ergodic or thermal state. If you want to have a picture in mind, look in the middle of the spectrum, and I like to say that all the states are the same. What does that mean? That means if you compute the expectation value of spin number 32 in your spin chain on this eigenstate, you will get a number, and that's going to be exactly the same number as the next eigenstate. So they all look the same. Of course, they are orthogonal, but they all look the same. All the same information. And in some, as a matter of fact, they respect random matrix theory prediction. Now, the other limit, which is a maybe more interesting one, is this many bodily localized state. And here I put different colors in the spectrum, which means the following. If you ask the eigenstate number, the red one, what is the expectation value of a spin number 32 in a z direction, you will get a number, 0.4, let's say. And if you ask the same question on the green eigenstate, which is at the same energy density, you will get a totally different random number, minus 0.2 or something like that. So this is against any statistical mechanics, thermodynamics, microcanonical ensemble expectation. Okay, so in some sense, all eigenstates are different. They do not speak to each other. And also, as we will see, they behave as if they were ground state. Important ingredient is that all the states are in the middle of the many-body spectrum. They're really not low temperature phase, not low temperature. All right, so what are these features of MBL? One thing you can look at when you have a spectrum is spectrostatistics. Oh, sorry, it went too fast. Okay, I don't have a picture here. That's a problem. All right, okay. So let me try to, actually I will use this other plot. So if you would compute spectrostatistics at low disorder, you will get something like level repulsion. You would get some measure of that, would be some number which will be large, which correspond to a random matrix theory. In a random matrix, eigenstates repel each other. If you go to very strong disorder, you would get Poisson statistics for the spectrum because essentially, as I said, all the eigenstates, they don't know each other. So we get some Poisson statistics. Sorry, some picture where I was off. I will try to put that on the slides on the PDF. That's the first feature. The second feature is very important too. It's the amount of entanglement, quantum entanglement, encoded in this eigenstate. If you are in a thermal state at low disorder, you have a large entanglement. This is normal because at finite energy, you have a quantum entanglement, entropy, which will actually behave as a thermal entropy, so that's extensive. That's what we call entanglement volume law. On the other hand, if you go to the second family of state at strong disorder, you have a very low entanglement. The MBL eigenstate, you can picture them essentially as product state with some limits, but it's something which scales, if you divide by the system size, which scales to 0. So it's a very strong difference. That's like a ground state in general. There are also many features. One of them, which is very important, is not about eigenstates, more about dynamics. That's very important for experiments. Something which I should say is that this MBL field also has been driven by numerics, by theory, but also by experiment, in particular called atom experiment, where we can do this very simple ansatz type of quench, where you start from some simple state like that, like up, down, here actually with actual particles here, and you let the system evolve according to its own dynamics, and you will find that there is a way in the MBL phase that you remember the initial state. Normally, if you're in thermal phase, at some point you lose memory of the initial state, you just go to the thermal ensemble. That's not the case here. You can measure that through some imbalance, which is a number between 0 and 1. If you stay in the same state, you stay at 1. And if you go to the thermal state, it would go to 0. So it is typical plots that are actually found in the experiments, up to some time scales, of course, because VC systems should be isolated. They're not perfectly isolated, but they're isolated up to a factor of 100 or maybe 1,000 hoppings by now. And what you find is that if you are in the strong disorder limit, you have a memory of the initial state. The imbalance is staying close to 1. You remember the initial condition, even at infinite time in some sense. And at weak disorder, you go to something which is very close to 0, which corresponds to the thermal state. There is no something is completely wrong with the slide. Okay, let me skip that. Okay, I think in the conversion to PDF something went wrong. I hope I will have more slides, but that's okay. So let me give you the status of the field back 3 or 4 years ago. So after a lot of work, around 10 years of work, we thought that we understood the MBL problem. we thought it from numerics. This is a typical phase diagram that we obtained back in the days. We thought we understood so with MBL state and ergodic states. There were experiments which were confirming all what this phenomenology I was talking about. There is even a one analytical and phenomenological fixed point, which is actually to understand the MBL states. They can be described as a state of matter with an extensive number of local integrals of motion. And there are actually even some analytical proof in some model. So it seems all fine, but then there was some kind of crisis about 3 or 4 years ago, where you can see very provocative titles like that. And if you read that sentence, that's very provocative. People thought that all was seen was maybe just a crossover and just a big fine size effect, if I want to summarize quickly. And I will show you what I'm talking about. So there was fine size effect in numerics. I mentioned these dynamics which were going to a non-thermal state. Maybe people say that actually very, very slow dynamics. And there's a new type of players, which are avalanches and resonances, which I will try to tell about. So fine size effects. So if you look at the spectral statistics, this is a plot actually I wanted to show, but we didn't come up in the talk. So this is a measure of the spectral statistics, this being random matrix ensemble, and this is Poisson statistic. This is some simple measure of gap ratios. And if you look at over the years, what were the numbers? Numbers were almost exactly the same, but if you look in a log scale, it's a bit nice crossing. If you look more carefully, as we did here, you see that the crossing actually shifts with increasing system size, up to the point that this group of people try to actually collapse the crossing by actually dividing the disorder by the length, which means that if you believe that there is a crossing here, you believe that there is no MBL because the critical disorder would go to infinity. If you do a different job by looking at all this crossing scale as a function of 1 over system size, you actually extrapolate to different value, finite value. We did the same for entanglement entropy, which was this volume law versus area law. There is a shift in the crossing here with different system size. I should, of course, emphasize, we had a talk with, we have like 10,000 particles, something like that. We can only live with 20 or 24 quantum spins, but that's very huge Hilbert space, as a matter of fact. But this crossing actually drifts, but if we extrapolate the crossing, it seems to go to a finite value. So there are some finite effects which we don't fully understand, but in some cases, we think we can extrapolate them. The other criticism came from slow dynamics. So I was mentioning this imbalance dynamics, where the imbalance in the MBL phase would go to a finite value, depending on well, here are different types of disorder, I think. Yes, different types of interaction. Well, I'm not sure. Anyway, people saw that actually, if you look very carefully at these curves and you try to extrapolate, look at the scale here, extrapolate a power law here, actually this would decay. And if decaying to 0, if you believe the power law sustained up to infinite time. So people were thinking that, well, maybe everything that we saw was actually, so if you look at the eigenstate, we are the critical point at 4, maybe 5. People would actually think that if you look at on longer system at dynamics, you would actually have very slow dynamic, but still ergodic, and the MBL point would be later. The MBL phase would be later. That's what this study said. So it's first controversy. And the final controversy, maybe try to reconcile all these viewpoints, came from 2 different scenarios, which I will just very quickly say. So people say that, well, you are on finite systems and you have this local integral of motion picture, but that cannot explain everything. In particular, there are 2 mechanisms which cannot be explained, which are the following. So let's say it's a question of avalanches, not the same one in Valentina's talk, but the same idea maybe. So the idea of the phenomenon of this instability, which is very hard to see, impossible to see in the numerics, as far as I understand now, is the following. Let's imagine you are in a random spin chain and you have these very well localized spins, but for some reasons, a few spins are not localized. For instance, if there's a small disorder at this portion of real space, some kind of ergodic grain or ergodic seed, and these spins interact with some interaction scale which is actually dictated by some location length. And the idea of the avalanche is that maybe by direct interaction, this spin, the blue one, will summarize, and then will make a stronger bath of 3 spins. And then that will grow on, and eventually, in order to summarize a longer system, a longer bath, and so on, and maybe the full system. And if you go through the idea and the argument, the claim is that if the initial localization length, the one from the bulk, if you want, is larger than some threshold, which is epsilon star, chi star, I'm sorry. There is some number, depends on the model, but there is a number, a finite number. Eventually, the system will delocalize and summarize in the thermodynamic limit. So that's the avalanche argument. And that's very specific to 1D. I should have said that MBL so far is understood only well in 1D, even though in 2D there are some slow dynamics which resemble MBL. So that's this idea that this non-perturbative type of avalanches will make the system thermal as long as you have a large initial location. That's something which, unfortunately, as I said, has never been really observed. It has been put by hand. This ergodic, this kind of put a bath by hand, and people throw stuff, but in a microscopic model, this has never been seen. The final ingredient, which is maybe missing in this local integral of motion, in these many-body resonances, is some kind of direct coupling between eigenstate, which correspond to some cat states like that. I think Nicola will mention that a bit more. There are some hints of that, but it's very hard to see them in practice, especially because these resonances imply a large number of spin flips. Okay, but what I want to conclude this introduction part, I hope I will have time for my own result, is that this is a scenario advocated, the most recent scenario advocated by Morningstar, David Hughes, and co-workers, is the fact that what we thought was an MBL transition is actually a crossover, not to an MBL phase, but to a pre-thermal MBL phase, something which on any finite size or any finite time observation window will look like MBL, but it will eventually not be MBL. And maybe there is some MBL critical point, which we don't understand really well in terms of RG, for instance, but it has never been probed so far. And yet, these people try to put numbers between these different energies. Okay, so this is more or less our status. If you want, I will take questions at the end of the talk about that. There are some evidence we don't fully agree with these numbers and even with the scenario, but I will talk about something else. I will talk about this very initial question which ignited the field. What happens if you just take the Anderson insulator and put a little bit of interaction? Are we going to be ergodic or are we going to be MBL? That's a very simple question, which I think I was never really fully so far understood, because people thought mostly about this large interaction limit, because to see the main mechanism at play. But this question is, I think, very interesting. So this is actually related to the avalanche argument, which I was mentioning. So this is the location length of the pure Anderson insulator. As a function of disorder, it diverges as one over disorder square here at weak disorder. And if you follow the argument I gave for the avalanche, I said that if the initial localization length is large enough, no matter what happens, you will summarize in thermodynamic limit. So if you take this finite value, there may be some uncertainty here in the definition of the localization length, but it will predict that there is a critical disorder below which you cannot be MBL. Okay, I just took the criterion and applied it to the Anderson case, of course, assuming that the localization length will increase with interaction, which is very, makes sense. So this is some sort of prediction, and we can now want to try to test that. This is a scenario. That's what we will end up having, but now I will show you numerics which validate this scenario. Okay, what we do is actually do the standard thing. We look at all these markers of MBL, entanglement entropy, spectral statistics, some other quantities, and we just go to weak interaction and try to scale with system size. We can look at the entanglement entropy divided by L as a function of very weak interaction for different system size. And you see that the drift is drifting towards 0 for a fixed value of disorder. We can chain the different observable, all the things drift, and if we try to extrapolate the drift, we see, so this is a critical disorder at critical interaction at which things cross here, these values cross, it goes to 0 in this way. So which means that at disorder 1, where the non-interacting localization length is around 2, we have no MBL. We can repeat the analysis with by, yeah? It's Kullback-Leibler divergence between the Poisson and the actual statistics of the gap ratio. It's yet another measure, and it has two different limits: 0 for Poisson, and of course, because that the distribution will be the same, and some finite value for GOE. So if it goes to 0, it means it's going. So wait. Sorry? You're not at, it's very far from random matrix theory. No. This phase here will win with system size. So that's GOE. No, it perfectly matches actually. Yeah, perfectly up to finite effect. So this has very weak disorder. If we increase disorder, we have the same. We repeat the analysis. Crossing points are there. They drift with system size and they extrapolate to 0. If we go to a slightly larger disorder, well, it's hard to say here. Maybe it's a finite or 0, but this is where we found the boundary. We did numerics not only at finite, at fixed disorder and changing the interaction strength. We also did things that by fixing the interaction strength and changing the disorder, and we can also extrapolate, yet with a different power law, to a finite value. So in the end, the phase diagram that we obtain is the following. This is actual real numerics, not just drawing a line on a blackboard. This is interaction of disorder for this x-axis spin chain. And we find, indeed, that if you start from weak disorder, and if you increase a little bit the interaction, you don't jump to MBL. So this line is the Anderson line, once again. You immediately go to an ergodic phase. And our experience with numerics that if on finite size you see ergodicity growing up, then there is very, very few chances that actually MBL will show up. So finite size effect always go in the direction of being more ergodic than you thought on smaller system size. But here we still find MBL. So this is this new line. The critical disorder is between 2 and 3. It's hard to say, but we are pretty sure that here we have a finite value for this critical disorder. So I think I will just end up with the questions you all have in mind, I guess. Actually, that's going to be my conclusion. So is a critical disorder, you find the one predicted from avalanche theory? No, it doesn't have to be. We don't test the avalanche theory here. We just say that we have a critical disorder here. As a matter of fact, the avalanche theory will be a lower bound. Maybe it will be here. We don't know actually. We cannot say that our results validate the avalanche theory. At least it does not contradict. Well, question you have in mind, you mentioned finite side effects. What about finite side effects in your study? Well, maybe there are, but as I said, if we were able to do, I don't know, 30, 40 spins, which is essentially impossible nowadays, maybe things will change, but the R-star can only increase. So the result that at weak disorder, we can only transit to ETH, ergodicity, I'm sorry, is very strong, I think. And finally, since I mentioned here, all this study was based on eigenstates. really diagonalizing essentially as a big matrix. Now we can also do something else. We can look at the dynamical signature of this phenomenon. I mentioned experiments do that, and in practice you can also do that on your computer. And this is where I mentioned this work with Oshmi right now. We try to check this phase diagram with a dynamical probe. Again, with this imbalance type of plot, where you have imbalance as a function of time, according to different parts of the phase diagram. For instance, if we go from, let's say, intermediate interaction to weak interactions that correspond to these lines here, you see that the imbalance at a strong interaction actually goes to 0. Maybe it's not 0 here because it's a log scale, but it goes very low, and you can check finite size effect here. And then if you increase, if you go along these lines here, going towards a wing interaction, of course, the imbalance stays a bit stronger, but it still plateaus to a very small value, which will decrease with system size. So this line here, we can probe with the dynamics, it's the same result. We also are trying right now to see if we can find the phase transition along that line with dynamics. We confirm that this point here is going to be thermal, that this point here stays MBL. This is an imbalance memory, this memory of the initial state. And here, this is close to where we find a transition line. There are some subtle finite side effects. The imbalance has dropped by a factor of 2, but it's still finite. So we are working on trying to establish if we can refine this line. And I think I will stop here, and I will take questions. Thank you for your attention.
So thank you very much. I mean, could you just make for the non-initiated a comment on higher dimensions?
It's unlikely, well, the exact results are only for one dimension. This is where we have the more handle from numerics and analytics. And, well, it is thought that if you increase the dimension, you give more space for interaction and ergodicity. It is thought that the MBL as a phase is not stable, but in higher dimension. But experiments and dynamics on small system size, they still see signature of localization, but it's more likely to be a transient effect. So yeah, in high dimension, we don't expect MBL in general.
Okay, so you said that this the island picture has not been seen in so far in simulations. Is it like you don't see these islands of ergodic and
okay, so what people have done is the following. They have planted by hand some, for instance, they take a disorder 20 for the chain, and for few spins, they take a disorder 2, which is like ergodic. They have planted and they have tried to see if the thing grows in time, and it does not that much. So, and the other thing which people have done, and I think where they see some kind of indirect signature, they don't put really low disorders, they really put a bass. So it's a different setup. And there they deduce, they force the avalanche in some sense. They look at the bass, that's the lowest I say, lowest gap of the couple system, and they see some signature, but that's not really, they force in some sense the avalanche to run.
Yeah, but so it's maybe the fact that you're a small interaction isn't like an occasion to use like perturbation theory, like to go to higher.
This was done. This was done already by Basco, Reiner, and Schuler, but it's very hard to be exact.
But numerically, for example,
sorry?
you could use like effective numerical methods, like you could.
Diagrammatic?
Yes.
This has never been done. This has been done analytically, and you can resum some of the diagrams, not the others that you forget. But I don't think there was any remember that we don't start from a low energy state. You should start with a full, you're interested in a mid-spectrum eigenstate. So maybe that's more difficult for perturbation too, but maybe it's possible. It has never been done, I think.
Thanks for a very nice talk. So, so you're looking at the situation where in the non-interacting system, all the states are localized, right? But if you look at a system where you already have single particle mobility edges, do you think that the states which have larger localization, I mean, do you think still there is a critical energy when you turn on the interaction such that states which have comparatively larger localization length, they will immediately get delocalized, but others will show a transition?
If you believe in the avalanche criterion, yes, it would. That would be exactly what you say. Even though for the system you have in mind, they don't have a true random disorder. They have no rare events, I think. Quasi-periodic systems do not have. So they might have a different phase diagram at weak interaction. This is not known. This is very interesting to see if that would be a discrimination of whether this H star that we find, is it the same as the one from avalanche? Actually, yes. So it's a very interesting question. I don't have the answer.
So if the,
So you hinted at the fact that you believe that this pre-thermal phase is not there even at higher interaction.
It's not a well.
Or that, let's say, the scenario
we have a real. I think. Okay. So what? The fate of this thing, we see that in the numeric. We see some very slow dynamics and so on, which are maybe a bit different from here. Whether it will stay as a phase or it's a question of how you look at rare events, or if you focus on rare event or on the average as typical, there are some interesting effects here. Nicolas will be talking about that. Whether it persists at a phase, I don't think so. Actually, I think maybe this is a bit on the right, but I don't think there's a. I really think there's an MBL phase we can probe on our fine size numeric, the true one, not the pre-thermal.
Okay, thanks.